a inglés, well, it is a great pleasure for me to introduce my colleague and friend, Anton Wakolbinger. He obtained the doctorate at the University of Linz, Austria in 1980, where he was teaching several years. And later he joined the Department of Mathematics of the University of Frankfurt in Germany, where he is professor. He has also been director of the Institute of Mathematics at the University of Frankfurt. He has had a strong leadership in probability, not only in Germany, in organization of conferences and international organizations such as the Bernoulli Society. His main area of research is random branching populations and applications to biology, with numerous papers, books, and students. Anton and I started working together on branching systems at the University of Linz about 33 years ago, where we wrote our first papers, some of them with Sylvie Relief from Paris. He visited our department in between 1988 and 90 for a year or more, and at other times. He taught a course here on random branching populations and wrote a book based on the course, which is published by the Mexican Mathematical Society. I had also been working on branching systems with Tom Dawson from Canada, and later on, the three of us joined forces in writing other papers on the subject. Anton has also published papers with other people from Mexico, Jose Alfredo Lopez Mimbela, Adrián González Casanova, including a paper with him that won a prize, and Ariam Blancas. The title of his talk is Evolving Genealogies for Branching Populations under Selection and Competition. Okay, go ahead.
Thank you very much, Luis, for this so nice introduction. I feel very honored about the invitation to speak on the occasion of the 60th anniversary of Universidad and its Departamento de Matemáticas. And what you were saying, Luis, meets my first slide. This is a short timeline of my Mexican connections. So this was the 4 months visit in 89-90, which was very important also in my own development. I learned a lot of new techniques. I also met many interesting people, among them future collaborators. And here are, with some color coding, the papers which I wrote, which I had the pleasure to write with Mexican co-authors. With you, Luis, with Jose Alfredo Lopez Mimbela, with Adrian, and with Ayram. The latter two belong to generation 3, I would say, because Jose Alfredo is more or less, well, he's younger than me, but I would count him more into my generation. And this last paper with Ayram is the one, and with 3 other co-authors, right, which I should mention also, Stefan Kufler, who recently returned from Israel to Frankfurt, Sandra Klim, who went from Frankfurt to Leipzig, and Viet-Chi Tran. I'm quite proud that we have also Viet-Chi Tran in our quintet, as we say, because you will see it's a sort of invasion of a way of thinking into the French world, I would say. And yet she was very important as a sort of also critical co-author, whether this should meet with all the techniques they had already and so on. Okay, today's lecture is on this recent paper with this one here, right? The recent one. And it has the same title as the lecture, this paper. What we will do is we'll construct the joint evolution of the population size, the type proportions, and the genealogy in a continuous state, multi-type branching process, but not the usual branching where everything goes independently, but it's a interactive branching. It's a branching with selection and competition, right? And to keep things as transparent and easy, I would say, as possible, I will restrict to a prototypical example with only 2 types. In fact, it's this example which we worked out in the paper in all detail, right? I can give an outlook at the end on the class of models to which the techniques apply, but let's stick to this system. So what does this system do? You see, we have here something I will comment on in a minute. It's the Feller branching term, right? And we have a determinist, so to speak, a drift part, which says that the red type, the alpha type, is just growing, right? That's a supercritical term. And the red and the blue type, they are competing, right? That C for competition. You can imagine that pairs of people meet and just one kills the other, right? It's a sad thing, but here the blue thing just is similar, but it does not have this supercritical thing. It's not selectively advantageous, but also competes in a symmetric way with the red one. Okay, so these coefficients are the coefficient of selection and the coefficient of competition, right? Of the one is of type alpha and the other mutual. Okay, I said already, the prototype of a continuous state population size process is Feller's branching diffusion, right? You could just think of here, maybe this logo that we have here, the time, and we have here an initial population, and then this diffuses, and it might eventually, and it will eventually die out. So we have here the psi of t. And it's driven by standard Brownian motion. And the fluctuations are proportional to the size. More precisely, the infinitesimal variance is proportional to the current size, right? That's the diffusive limit of a good old critical Galton-Watson process, right? When we scale time so that we have many generations and small mass, then this comes out as a diffusive limit. Now, one can say this is a mass, right? This is mass which we are recording here. Where is the genealogy? Well, we could of course go to the limit and say when we have here a mass psi of t, we might sample individuals from this mass. But this is of course this needs an explanation because we might the genealogy is not here a priori, and one might also wonder what purpose it serves. We will see that it serves a very good purpose when we have these more than one type interacting, competing. Then genealogical considerations are very valuable. But let me just anticipate that when we would go to the limit, start with a particle system and do this scaling limit, then in the limit, one detects a Poissonian structure in the genealogy. Looking back, one detects nothing else than Kingman's coalescent, but with a time change which is given by the current mass. You can imagine like this: when the mass is big, then two randomly sampled individuals take longer to find their common mother. When the mass is small, or even a bottleneck is there, then the time is quicker to find the mother. That will be the time change. And since I'm speaking of Kingman's coalescent, I must give you a very quick glimpse on Kingman's coalescent. And I will just zoom into the important stuff for what follows. A nice, but also far-reaching way to picture a nested sequence of Kingman N coalescents, right? First 2 leaves, then 3 leaves, 4 leaves, and so on. This is what already can be found in Kingman's seminal 82 paper. It's called the natural coupling by Kingman, right? And let me just sketch it here. We go back 1 lineage, then we go back a 2nd lineage, and after a standard exponential time, this coalesces into the 1st lineage. Then we go back a 3rd lineage, and this independently with standard exponential clocks coalesces either into the number 2 or the number 1, but of course only as long as number 2 is here, right? So when it's here, then it cannot coalesce anymore with 2. It can only coalesce with 1, and this it does with an exponential clock of rate 1. Okay, now a small step is to say, let's draw this tree in a nicer way, right? Because we just want to save room, right? That is, when here there are only 2 lineages left, why don't we put this lineage over here, right? Then we have saved room where I can write something or whatever, right? And actually I do this here, right? I've saved some room. I can mention a historical note. This is a cutout of the so-called lookdown graph, which is described in words and of course used very, very intelligently in Donnelly Kurtz, and which Peter Pavlov and I also used in order to study the most recent common ancestor process of an evolving Kingman coalescent. Look, the difference between this and this here is just that the coalescences are marked with arrows. And as I said, this line is just shifted over there. Now, in 2000, Evans wrote a very nice paper, Kingman's coalescent, Steve Evans, right, from Berkeley, Kingman's coalescent as a metric space. And this is just the natural numbers where one can put a metric on. And this metric comes from the genealogical distances of 2 individuals, say 2 and 4. They have the genealogical distance. We go back and ask, how long do we have to go back until they meet their common ancestor? And twice this distance is twice this time is the genealogical distance of these two individuals. So this is an ultra metric. That means we can just picture it as a tree, right? And we can then, following Evans, look at the completion of the natural numbers with respect to this random ultra metric. And things become even nicer when we put a measure on the leaves, right? The measure on the infinitely many leaves. And this is then the weak limit of the uniform measure when we go to n plus 1, n plus 2. But weak always needs a topology, and the topology is here this random metric, right? And nicely enough, this weak limit exists almost surely for almost all realizations of Kingman's coalescent. This weak limit exists, and it can be thought of a natural probability measure to sample from the top of the tree, right? That's the measure which one should have in mind when one says, let's sample from the mass of a, say, Feller diffusion at time t, right? And all this has been very nicely worked out in actually two papers in EJP of Stefan Buffler, also one co-author in the quintet. And he exploits the fact that R is exchangeable. Actually, although the R is constructed from this picture, it is, as one can see quite easily, exchangeable. That is, its distribution is invariant under permutations of the i's and j's, right? And even nicer, the Rij, which is random, right, has the same distribution as the R randomly sampled capital I randomly sampled capital Ij, where they are drawn from this sampling measure, right? That's non-trivial, and it's also relying on the theory of Werschik and Gromov on the representation of trees in terms of their distance matrix.
Professor Anton, sorry, yes. Is it possible to hide a gray rectangle appearing in front of your slide? Because it's not, I don't know if the other, it's a kind of volume and
my
recording.
Assistant and friend Jan Lucas. There are these ghost rectangles sometimes in the Zoom transmission.
Oh, I believe we can't do anything serious against that.
Or should we just reboot or restart or what?
No, I know we can restart the screen sharing. Sometimes that helps.
Right.
No,
so,
I think this is the problem with the sharing from the iPad. I think.
Yes. I'm sharing from the iPad.
Yes, exactly.
Yeah, I think this will be there forever.
Yeah, probably.
But
okay.
It's a new bug. We didn't experience this bug in the lecture. So
I see. So I mean, when Jan Lucas says, when Jan Lucas doesn't know it, then this means that we cannot fix it.
Okay, no,
but it's very small. It's okay. It's small.
It's small, yes. It's just it has at most one row. The presentation, but it's okay.
I'm sorry.
We can follow.
If something comes then hidden or not clear, please just ask. I can then maybe pass to another viewing mode. Should I maybe try to shift?
Yes, maybe continue.
Yes, I will do that. So Anzeigen nahtlos. Right. I mean, probably that's then if I move here slowly, then this might be.
Yes, it's better. Yes.
Yes, that's correct. Yes,
that's correct. Thank you. Thank you.
Thanks for the hint. Now, we so far considered the coalescent back from a fixed time, right? We had a fixed time where we sampled all the leaves, and we had the Kingman coalescent back from that time. Now we consider all times simultaneously. And we have a random, a source of randomness, a natural source of randomness, which drives all the things. And these are these Poisson point processes of arrows from I to J. Remember, we had them here, all these arrows coming at rate 1 per pair. And that we do now, we draw the entire lookdown graph, and on top of that, we have now a ultrametric on the set R plus times n, where again we trace back the ancestral lineages and have here those coalescences and measure from two of say I and J. We go back and say this is then the distance, right? Just as we had it before. And two individuals that are connected by an arrow, right? Two individuals that are connected by an arrow, this one and this one at S, so this would be Si and this would be Sj. They are decreed to have genealogical distance 0. So that means that here the J is a newborn daughter from the I, or the individual Sj is a newborn daughter of the individual Si, right? And as an initial condition at time 0, we say for simplicity, but that is not necessary. I do it just for simplicity here in the talk, that all initial individuals, 0i, 0j, and so on, they have genealogical distance 0. So they come at time 0 as daughters of one mother instantly. We might as well start with an exchangeable distance matrix as an initial condition. That's what we do in the paper. Now, a realization of this so-called look-down graph gives a random path of an evolving Kingman coalescent. We will see pictures later. I save time here not drawing this. But I tell you that what we have here, driven by a natural source of randomness, can also be described as a solution of a martingale problem. You see, in a martingale problem, you don't speak of the source of randomness. All is in distribution, right? And that is, of course, in a sense, more robust because it does not hinge on this special representation. You can draw a tree in many ways, right? You can draw it on the blackboard, you can draw it on the iPad, and it should be the same object. And so one speaks here of an isomorphic class of ultrametric measure spaces, and they also carry measures, sampling measures, and they should also be respected by the isomorphisms, right? And let nu chi be the distribution of the distance matrix of a sample drawn IID from the sampling measure. And this distance matrix distribution characterizes the isomorphic class. That's what I was alluding by Gromov-Werschik theory, right? The distance matrix distribution characterizes the distance relationships in this class. And suitable test functions to determine this are when you test a function of the distance matrix on which depends only on finitely many individuals. That's a suitable space of test functions. And here you see, all of you who like generators, you see what's going on, namely in the course of evolution, the distances of two individuals grow deterministically, right? When you go on here from time t to time t plus dt, that grows deterministically. That's this deterministic growth. And this here is a Poisson term. The theta ij means that you draw an arrow and decree the I and j to be of distance 0. So the j is a newborn of I. That's a Poisson term, right? And this is the generator, first drawing and then doing the step. That's the generator of this tree-valued process. And in fact, Greven, Tafelhuber, and Winter, they did a completely different approach from this Kingman, evolving Kingman picture. They studied this martingale problem, and by tightness arguments and by duality, then they proved that this martingale problem is well posed. And Gufler, in one of his EJP papers in 2018, showed that the solution of this martingale problem is represented by the evolving Kingman coalescent, which is constructed on top of this Poisson point process L of look-down arrows. Let's call them look-down arrows. That was the terminology coined by Donnelly and Kurtz. Now, I repeat myself. I said the exchangeable evolving genealogy that underlies a standard branching Feller diffusion is represented, because of Gufler's result, as a time-changed evolving Kingman. Well, no, Gufler did not look at the Feller branching. He just looked at the Fleming-Viau situation, where one has a constant mass, but then looks at the evolution of the families below that. Now, when we have a fluctuating population size, we bring in this time change, which is familiar, by the way, from classical papers by Etheridge, March, and Perkins. That's the time change between Feller and Wright-Fisher. And in fact, I recall this here. And this makes already this claim that the underlying genealogy is given by the evolving Kingman coalescent more visible. Think of two independent Feller branching diffusions. Then, as a matter of fact, the relative sizes of the, here this should be a beta. These relative sizes are time-changed Wright-Fisher diffusions. And Donnelly Kurtz gave a very nice representation of this Wright-Fisher process in terms of initial coloring by a mu0 coin tossing and type transport by L. At any time, the what is then a Wright-Fisher process is given by the proportion of type alpha individuals at this time changed S of t, right? One must always go with this time change between the time of the Wright-Fisher diffusion and the time of the Feller diffusion. And the key fact is that the colors are exchangeable at any time. This is preserved. So here, this is a logo where we would have just one arrow, right? Then these types would be transported in that way. Or we could rather think backwards and say, go back and look, where does this individual originate from? And that's the type it carries. Now we go serious and we turn to our prototype case in which the type frequencies interact with the population size, right? That was not the case in this example we just had. And now adding the two equations gives a non-autonomous equation for the total mass, right? This is non-autonomous because it carries the component sizes. Now again, we can take this time change, the magic time change between Feller branching diffusion and Fleming-Viau, I can say, or Wright-Fisher in the case of two types. And then this time change process, that's the zeta, which I just, it's the same as the psi up to the time change, right? This obeys a non-autonomous SDE, again driven by a Brownian motion, which is now different from the original one. This is non-autonomous. But, and that's the key message, it turns out that in an individual-based picture, for the evolving type configurations that are driven by the look-down arrows and an additional driver, which we describe in a minute, an additional driver for the selective and competitive events, then one obtains an SDE for the joint evolution of the total size and the type configurations, which has a strong solution. This is in the spirit of two papers of Donnelly and Kurtz, 1999. One was treating the case of constant population size and selection and competition. The other was treating the case of variable population size and neutral evolution. And our original motivation to write this paper was to marry these two papers, right? Because we simply didn't know why Peter and Tom hadn't done that. And I was extremely proud when I gave this a pre-version of this talk, actually already 3 years ago. We fought for this paper quite a lot. But now it's on the archive and it's submitted. 3 years ago, I gave a pre-version of this talk in the presence of Tom, and I asked him why they hadn't married these papers, and he said, well, simply because we didn't know how to do. So that was a technical issue, which we'll see very, very soon. Now, the intuition behind the individual-based picture is that we have this selective events, and that should be that any individual dies at this rate here, and its line is continued by the daughter of an individual randomly sampled from all beneficial individuals, right? That should be the effect of selection, which is already present in discrete models. And there should be the effect of competition that a type alpha individual dies at this rate, and a type beta individual dies at this rate, and is continued, the line is continued by the daughter of an individual randomly sampled from all contemporaneans. Now, this must be made rigorous, and this is done by a family of Poisson point processes on all the lines which drive these selective events. And they have four components: the time, the activity which triggers then the interaction, a seed of sampling, and a symbol which is either the star or a cross, which means either there is a selective event or a competitive event. And we write for a type configuration G, alpha comma beta to the n, right? So a colored configuration. We write this limit of the type proportions provided they exist. And it turns out that in our construction, the random type configurations do have almost surely these type proportions. Now, the update rules, which I described verbally a minute ago, they can be formalized in this way, right? This controls the right rate of selection. This controls the right rate of competition. And we also look to sample correctly in order to respect the update rules described earlier. And this is here a logo, which a picture says more than many words. And so here we have the old look down thing with the green arrows as before, but now we have additional events, the crosses and the stars. And when they are active means that this condition is met, then the line is continued by the daughter of an individual sampled randomly from the population. And the first theorem says that the stochastic differential equation driven by, well, the input for the total mass, the green look down arrows, the neutral thing, and these point processes K for the joint evolution of the total mass and the type configuration that arises from this non-autonomous SDE, but now with the mu GS, right, of alpha and beta figuring here, coupling the zeta with the G, right, coupling the total mass with the configuration of types in the look down picture. This SDE, this together with the above stated update rules for the type configurations has a unique strong solution, right? And it's really strong because the sampling seed comes with the K, right? This is a uniformly distributed W, which comes here with the K. And this is by the inversion, by the good old inversion method, it's used to sample from the type configuration, from the type proportions. Now, a very short glimpse on the proof. We apply an iteration scheme. That is, we start out with the neutral situation, we take the type configuration, we take the type proportions or the type configurations even that are only induced by the neutral arrows, ignoring any effect of K, and construct a first, so to speak, iteration of the total mass with these preliminary type proportions. Now we do a feedback loop, right? We determine which points of K are active using this pair in the update rules. Then we update the coloring using the rule that whenever we have an active point, it transmits its type, because there we have a newborn daughter, right? That transmits its type. And this, of course, again, doesn't fit, because then we have changed one thing and not the other, right? And so we have an iteration scheme, but miraculously, this iteration scheme converges. This was technically the most difficult part of the paper. Now, the message of theorem 1 is that the initial condition and the source of randomness, a Brownian motion and two Poisson point processes, prescribe a well-defined coloring of this time times the levels, one can say 1, 2, 3, 4, 5, this. And the types are inherited along the green arrows. And at any active point of K, the newborn passes its type on to its descendants until a new active point is met, right? So this has a unique, strong solution driven by this triple. Now, we didn't speak of the genealogy in an explicit way by now. It was lurking in the background, because we spoke of newborns from mothers sampled from the population. And in the papers by Donnelly and Kurtz, somehow this genealogy is present, but they also don't make it completely it's in some late chapters where they also comment on the genealogy, but it hasn't such a central role as here, namely when we include the selective genealogy, we have to recall the intuition behind the updating, right? Again, the type of the newborn individual at an active point of this Poisson process kappa is inherited from a mother that is sampled from all contemporaneans of type alpha if gamma is the symbol is a star, right, standing for a selective event, and is sampled from all contemporaneans and not of type alpha, but of any type, if gamma is a competitive thing. That has to be corrected, right? And it turns out that the coloring of the this set extends in a unique manner to a coloring of the completion at any time, right? And the sampling measures that are built on top of the neutral look-down graph, they allow a sampling of individuals that is consistent with the update rules at the active points. That means when we only use the neutral sampling measure as constructed by Gufler 2018, we can do this procedure not on the in the way of type distributions, but really with ancestral lineages. And so we can lift the story to the marked distance matrices, also in the selective setting, and we arrive at the next theorem, which includes also the distance matrices. You see here we have our full triple. We have the total mass, the distance matrix process, and the type configuration process, again driven by the same source of randomness that arises from the same non-autonomous SDE for the total mass, together with the update rules of the type configurations as we had it, and the distance matrix, right, has a unique, strong solution. And here I should, so to speak, complete the picture. I can do this here and say, when we say that this lineage comes from, as a newborn one, from this mother here, then we can trace back the ancestry of this mother back into the finite world. You see, that is a individual in the closure of the natural numbers, right? It's far out, infinitely far out. But the space is connected by this metric, and we have individuals in n times r plus that come arbitrarily close to this, and the ancestral lineage is well defined. And so we can trace back this ancestral lineage and redefine the genealogical distances and have this theorem 2, which I showed already, right? A unique, strong solution of an SDE for this triple. Now, we are already in the final act, and the final act will tie in with what I could call Greven's world, or Peter Pfaffelhuber, Anita Winter, Depperschmidt. I mean, they are studying, also Sandra Klim, I must say. She also, that's my second proud experience, that also Sandra, maybe that was even more important to convince Sandra that this explicit construction, like the sources of randomness and the lookdown graph and driving an SDE, which has a strong solution, are really competitive with martingale problems, right? But of course, one can now tie in. And in the final act, we will remove the ordering, which is inherent with this look down story, inherent with 1, 2, 3 up to the natural numbers, and thus passing to a process taking again values in the isomorphy classes of marked metric measure spaces, right? Going away from this very specific way of drawing the evolution to the robust description which only hinges on distance matrix distributions. Again, the adequate framework is no more that of SDEs, but of well-posed martingale problems. And the first step is to extract from theorem 2 a well-posed martingale problem for this triplet, right? So theorem 2 is an SDE. Here we, as we say in German, I don't know if you can translate this. Ross und Reiter wird benannt. So the horse and the rider is named. Of course, one could say the horse, this is the source of randomness, right? And the rider, this is this process. It's a strong solution. But here we only, with martingale problems, we only have an operator, right? Which is a surrogate for the generator. We don't need to dive into Hille-Yoshida theory. Actually, we had thought that we must dive into Hille-Yoshida theory, but at some stage we discovered that stochastic differential equations do the job, and then we can go over from SDEs to martingale problems. That's what we do in this proposition. Let A be the operator on a suitably chosen domain that corresponds to the dynamics of the SDE, right? Which we just discussed. Then the martingale problem is well posed. I would say this is a sort of wisdom of life, right? That when you have a unique strong solution of a SDE, then the martingale problem you can cook out of it is well posed. But you see, it's not just a remark, but it's a proposition. And we had to look very closely into one of the Donnelly-Kurtz papers, where they do an awfully short proof of a lemma, which actually where we could learn a lot how to do this, because this needs two steps, and I didn't write this, but I just tell it. First, we must extend our space here to the points. Actually, we must include the points of L and of K, right? The driver points. And this can be just translated then into a martingale problem. Then we are back to point processes and Poisson jumps and so on. So this is an intermediate step, which lemma, which I didn't. And then from this lemma, we can project by Kurtz's Markov mapping theorem to this coarser thing, right? That seems to be an interesting thing, which one might be used also in other occasions. Well, to just show you the generator, I don't want to frighten you, but this is the generator. Right? We saw the update rules, that was the SDE, and here is the generator, and this thing in black here, right? The thing in black is the thing we saw already, right? Maybe I highlight it again in blue. It's this. If we would have here just this, that would be Fellers branching diffusion, right? The generator of Fellers branching diffusion. And here we have the same generator which we saw in the Greven-Pavlova-Winter thing, right? So it's the neutral growth of the tree. But then come these sampling terms, the selective and the competitive sampling. It's just a rewrite of the picture I showed you, right? You sample and you do your update of the types and your update of the distances. Well, and now the last step, we have here a refined description, too fine, because we have all the orderings which we want to forget, right? So we go again to the space of isomorphy classes of marked ultrametric measure spaces, marked because all the leaves also carry their type, right? And again, we have the joint distribution of the distance matrix and the type configuration of an infinite sample drawn from the population. Very much the same as we saw it in the Kingman evolution story. And we build again this generator blackboard bold A from these test functions, and the theorem 3 says that with the omnipresent time change, if yt is the isomorphy class of the distance matrix process and the type configuration process, then the translation of the total mass with the time change gives the unique in-distribution solution of the martingale problem for the operator A and the domain D, stopped before extinction of psi. So it's in fact a stopped martingale problem. And the proof of theorem 3 is a case for Kurtz Markov mapping theorem, because by the proposition, the martingale problem for the refined process, for the representing a process, is well posed. And the isomorphy class of this one is given by the distribution of the marked distance matrix. This gives the mapping in Kurtz's Markov mapping theorem. You see, Kurtz's Markov mapping theorem has a mapping and a kernel going from fine to coarse and back by the kernel, right? And there is an important condition already in the discrete little sister of Kurtz's Markov mapping theorem. That's the, the pioneering result of Rogers and Pittman. And they have an intertwining condition which says that the coarsening, the mapping, must be compatible with the dynamics. That means when you are coarse, you must randomize, go back to the fine, right? And then you do your step, and then you do the mapping again, and that diagram must commute. But this is here built into the definition of the A, right? That's just built in the definition of the A, and things work because of exchangeability, right? Now, take this picture, and here is already the thing which I drew before by hand. You can follow the genealogy, sample the mother, go back to the next inactive point, sample the mother, go back. That's your, in one picture, the evolving genealogy, and it represents what actually I think has not been done so far. Greven, Tafelhuber, and Winter, they also, I'm not aware of a result which would cover our theorem 3 because of this. Well, of course, I think they would manage because one can do tedious tightness analysis. But since we had Sandra Klim in our team, and she said she would not like to do this, and she was content with this way, I'm quite confident that this is also a new result. Now, this was it, and let me conclude by felicidades, Sinvestav, que cumplas muchos años. Yo espero que eso es correcto, ¿no? Luis, tú tienes que decirme.
Bueno, yo te agradezco mucho tu interesantísima presentación.
Thank you.
Ahora, quienes se encargan de preguntas son Héctor y Carlos, ¿no?
Right.
Sí.
I'm happy to receive.
Okay, so please feel free to ask anything, everyone. Por favor, pregunten lo que gusten.
Hi, I have some questions. The first one is if you can extend this model to branching processes that are not failure branching processes.
Good question. I mean, then one would have in the neutral tree, right? In the neutral genealogy, one would have also inner nodes that carry part of the sampling measure, right? It's not just the leaves, but also inner nodes that carry. And so one would have a look-down graph which has this sorting in of many daughters, right, to one mother, which has been done indeed, right? I mean, this generalization of the Donnelly-Kurtz work has been done, but it's on the level of genealogies, it has not been pushed so far as Stefan Gufler did it with the continuous mass case, continuous mass branching. But it's a very interesting comment, and actually that should I'm very positive that the program just goes through, right? So, but then one has this green look down graph starting from the beginning. It will have its role, right? I guess. And on top of that, we will have the selective thing again, right? But it has not been carried out.
And my other question is, in this one, you have 2 types, but can you extend to more types?
Right, and the second very nice question, that in fact is sketched in the paper, right? And I even prepared 2 slides. This is just, but I deliberately did it after the end of the talk, right? Because this does not claim to be a theorem yet, right? It's because you see, since we worked I think 3+ years, 3+ epsilon or whatever years, we said it's better to do this thing with the 2 types just as a sort of pointer right now. But you look, I can very quickly go through it. When we have a general type space, then the relative type frequencies are just a measure, like in the Fleming-Vio case, right? You have a measure, it's a measure valued thing, and we have the total mass. That is a sort of polar decomposition, right? The total mass, and when you divide by the total mass, you have a probability measure. Actually, this is a probability measure, right? And now we have, and it's good to have not only Tom around in spirit, but also Don, right? We say that Xi is an interactive Dawson-Watanabe process with fecundity function B, competition kernel C, and mutation kernel L, right? If it solves a martingale problem, right? We can write down a martingale problem for this interactive Dawson-Watanabe, and it's actually done in a similar way, but without competition, I think, in a Donnelly-Kurtz paper already, right? So this thing has been analyzed in several ways. It's not a new concept, right? But now we can ask, what is the genealogy here, right? Can one also have the martingale problem for the genealogy of this thing? Well, the same program works, right? We have here the total mass, and it's a time-changed companion. It's a non-autonomous thing, right? And we have even, because we have here also mutation, a third symbol that figures for mutation, right? So we have again our look-down skeleton, right? And on top of that, we have the decorations which carry the task of selection, competition, and mutation. And we have to define the appropriate update rules at the active points, right? So the program should work, but again, it's not checked in all details, but we said it's fairly clear how to do it.
Thank you. That's all my questions.
Thank you, Sandra. More questions, please? More questions or comments? Comentarios, preguntas? Pueden preguntar en español también.
Ah, sí.
Okay, well, if there is no more questions, please, you can unmute your microphones, please, and we can give a big applause to Professor Anton for his nice talk. Gracias, Professor. Gracias.
Thank you. And I should not forget to show you these flowers. They are bought by my wife today. She bought it. It's just a salutación de cumpleaños al Silvestre.
Muchas gracias.
Gracias. Thank you.
Ahí nos las mandan por DHL. Gracias, muchas gracias.
Gracias. So the next